This is Jack Jackson. This is the first of a series of videos on finding some derivative formulas using the shortcut rules. And we have 20 problems here, and each one we're going to find a first and second derivative. So that's going to be 40 derivative formulas we're going to be calculating in these videos. And I'm going to do a video on each one. So we're going to start with this number 1 here. So each one we're going to use the shortcut rules to find the formula for f prime of x and f double prime of x, and then the tangent line to the original function where x equals 1, assuming it's defined there, and then graph all 4 of those things on the same axes. That's what we're doing on each one of these videos. I won't repeat that every time, but here we go. Let's do number 1 and see what we can come up with here. So that is our function. Now by the way, I'm using software here to typeset this. This is called MathType, is the software that I'm using, and it makes it look nice and pretty when I'm all done. But a lot of what I'm going to be doing here is cutting and pasting things. So here we have a function. Now this is not the answer yet, but what does it look like for the derivative? Well, how do you know which derivative rule to even work with? Well, the key is to think about the structure of the formula that you begin with, and that's going to tell you which rule to use. And think about evaluating this function. What would we do? We put in an x here, we multiply by 3, then add 2. Take the same input, multiply by 4, and subtract 7, and then finally multiply those two things together. So the last step is multiplication. So one way to do this is to think of that last step. That last step is multiplication, so we need the multiplication rule, or in other words, the product rule. So if we do that, what does that tell us to do? It says take the first times the derivative of the second plus the second part times the derivative of the first part. Okay, so let's take that. I'm going to copy that, paste it here. Now let's do this. When we take this derivative, this part is just 4, and when we take this derivative of this part, it's just 3. Okay, so let's take that now, copy and paste here, and let's see, if we distribute this 4, what do we get here? So we're going to take this part here, distribute the 4, so this becomes 12x plus 8, and that 4 is now gone. And we take this 3 times this part right here and distribute, and 3 times 4 is 12, and 3 times 7 is 21. That one's negative, and now the 3 is gone. Now we can take this and do a little combining like terms. 12x plus 12x is 24 x's. We combine those together. And 8 minus 21, let's see, what's that going to be? That's going to be a negative 13, I believe. Okay, and so that is our formula for f prime at x. Or, another way we could have done the same problem is take an f of x, and if we're going to work with it in the form that it's in, we have to do it the way we just did. The last step is a product, so we use a product rule. But sometimes you can manipulate the expression before you start. So if we had rather, we could have multiplied this out, say with the distributive property, or you might know it as FOIL. 12x squared, first times first, see last times last, that's negative 14. And then we need a middle term, our x term. Okay, so let's see, we got 2 times 4x is 8x, minus, that's 21x. 21, 8x, and minus 21 is negative 13x. And then, if we want to do the derivative, I think you can probably just write it down. 2 times 12 is 24, and x goes down to the power 1. The derivative of this part is negative 13, and the derivative of this part is 0. So probably in this one, I would probably rather do it the second way than the first way. But of course, either way works just fine. Now, if we want to find the second derivative, okay, it's just 24. Alright, now how about the tangent line? Well, first of all, we need to find where whether we do it this way from the original or the other one, or from the reduced version, or not reduced, but expanded version. We want to find f of 1. So everywhere there's an x, we put a parentheses, and in that parentheses we put 1, like this. So a set of parentheses there. So that's just 3 times 1 is 3, 4 times 1 is 4. Three plus 2 is 5. 3 minus 7 is negative 4. And so that is 5 times negative 4 is negative 20. Okay, so that means that 1 comma negative 20 is on the graph. That's our point of tangency. F prime at 1, take this formula here, so our slope of our tangent line is f prime at 1, which we're just taking a 1 and placing it here. So that's 24 minus 13 is 24 minus 13 is 11. So we have the equation of our line, y equals m, parentheses, x minus x1 plus y1 is our slope of our line, and this is our tangent line. That's the slope of a line in general. It's a tangent line. I'm going to call it t of x instead of y. The slope is the derivative at the point, which is 11. That goes in place of the slope here. And the x is the x1 is the x point of tangency, which is 1. And the y is the y1 is the y point for the point of tangency, like that. Now we could multiply this out and write it in different forms, but I'm going to leave it like that. That's a nice form for it for our purposes. Okay, so let's see if we can graph all these things together. Okay, you might want to write those down, and I'm going to move them where I can see them off the screen here. Okay, so let's go in and graph this now, say in a graphing utility. So the first function we're going to graph is let's see here. Okay, now, what is it? The original function was, if we put it in the original form, it's y equals, parentheses, 3x plus 2, parentheses, I think I don't have the times here, but I will put it in there anyway, times 4x minus 7. I'm using the shareware program Graphmatica, which I highly recommend for doing graphs. So there's the graph with the original. This may not be a really great window. We'll have to experiment with the window in a minute. But there's the original. The derivative was 24x minus 13. So the derivative is in red. And the second derivative was a constant, just 24. Okay, and the tangent line is y equals 11, parentheses x minus 1 minus 20. Alright, so can't see all those things, so let's see what we can do to experiment with this. It looks like a lot's happening right here. Don't see so much on the edges, so let's go up or down quite a bit and play with the grid range here. Now we see that the x-intercept is at, well, this point of tangency is at 1, negative 20, so we need to go down, at least down, below negative 20 to see something interesting there. And, well, let's just try let's try experiment with this a bit. So let's go to our grid range. This is like the x min, x max, y min, and y max on your calculator. So let's come in a little bit here on the x's. This is not going to be a square scale. But let's see what happens with the y's. So let's go down to negative 30 to 30 and just see what happens. Okay. Uh-oh. Our tangent line seems to be off a little bit. Let's see if I did something wrong there. Oh, I see it. See where the mistake is. Okay, and here I'll show you where the mistake is. You caught it already. 4 minus 7. This should be 4 minus 7, and that should be negative 3. So this is negative 15. Okay, for the coordinate. And so that should be a simple fix. We just change this to negative 15 here. Okay, maybe you already caught that when you were watching me do it. Okay, so if I just take this one and change this to negative 15, see if that looks better. Yeah, that looks better. There's our point when x is 1, and it's a tangent there. And get rid of this. All right. Well, that's not a bad looking graph there. Okay, so what do we notice about this? Let's see. Well, here's the original function, which is a quadratic. It crosses the x-axis at a couple places here. We could use the quadratic formula to find those if we wanted to. It crosses the y-axis here at 0. Let me look back at my formula when we expanded it out. It was 12x squared minus 13x minus 14, so that should be 0, negative 14 right here. Yeah, that looks right. If we do its derivative, we get a linear, which is this red line here. Notice that it crosses the x-axis right about here, actually at 13/24, right there, just barely beyond a half. And that is exactly when the original function has a minimum. So the minimum when the derivative is 0. Okay? That being a straight line, it has a derivative which is just the slope of that line, which is a constant function. That's the green one up here. So maybe I should put some things on here. So we can place a couple labels here. This one's f of x. F prime of x is the red one. Maybe I'll put the label there. And then f double prime of x, that's the horizontal line. And then the tangent line I'm calling t of x, and I'm going to put it there. So now we can see these. I'm going to copy these graphs. This is one of the nice things about Graphmatica. I can go over here and paste that right into my graph, and then let me close out my equation editor, and you've got a nice looking solution there. Okay? We can kind of check our work by seeing that the tangent line does actually touch the point. It didn't when I first did it, and I knew I had made a mistake. I was able to catch it so that it touches when x is 1. And of course, if you zoom in here close, the graph of the tangent line and the graph of the original function should look pretty much the same, and they do right in here. So, looks like we've got a nice solution to that one, and we'll come back and do another one after this in the next video.